Good afternoon. Today we are going to do section 4.3, which is rational exponents and roots. So first thing you probably want to make note of is what's a rational exponent. And I know you're familiar with exponents because we've talked about that the last couple days. But if something is rational, it would be an integer that terminates or repeats. So for example, I could have x squared. I could have x to the 2/3 because 2/3 is 0.666 repeating. So more so, we're going to get into exponents today, like fractional exponents that you probably haven't dealt with much previous to this. Roots, you already are familiar with the square root. Now we're going to do other roots like cube root, fourth root, etc. So just kind of keeping those two things straight. You can go back and forth between rational exponents and roots, which we'll be doing today, but just to keep them separate for now. So I want to do probably what we would have you had done in class, is just kind of play around with y equals x to the 1/2. So if you picked various x values, right, like 2 or 7 or -4, whatever, and just kind of played around to see what would happen. So if you put it into your calculator, you certainly can, but if you put it into your calculator, into your y equals, and go to your table, you can scroll through and see more than the values that I have here for us to look at. But here's a few. Take a look at that. I mean, why am I getting the error when I put -1 in for x? Why am I only getting nice integers at 0, 1, and 9, and 4, right? There's some pretty nice integers right here, and here, and here. So those are interesting. So just, pause the video, take a moment to kind of make a correlation between those x values and when you raise it to a power of 1/2. So in other words, this is saying when x is 4, y is 4 to the 1/2, which apparently, according to my table, is 2. When x is 9, 9 to the 1/2, according to my table, is 3. And maybe you're starting to notice that these numbers are also perfect squares, 4 and 9, and when I square root them, I get 2 and 3. So is that saying that x to the 1/2 is equivalent to the square root of x? I do believe it is. Look at the rest of the numbers. Maybe you're familiar with the square root of 2 is 1.41, and yes, it is. 2 to the 1/2, same thing as the square root of x. Okay, so keep that in the back of your mind. Now if we go on to what about x to the 2/3? Okay, and I just took a snapshot again of my table of values, some various tables, okay? If you pick out the nice integers again, this one worked out nicely. Both of these did, as did this one. This one. So, for example, if I focus on 27, 27 to the 2/3 is 9, and 8 to the 2/3 is 4, just to kind of highlight a few. -1 to the 2/3 is 1. And what do you notice? Pause the video, take a second, see what you think. So maybe you noticed that all of these were perfect cubes. So for example, the cubed root of 27 is 3, and then 3 squared is 9. So maybe you notice that over here, if I do 8 cubed and then square it, so the cube root of 8 is 2, and then 2 squared is 4. Same thing with the -1. If I do -1, cube root of -1, and I can cube root negative numbers, right? Because negative times negative times negative is still negative. So that's still -1, but then -1 squared is +1. So maybe you were making these connections. So if you did, how would you figure out what 49 to the 3/2 is? Not 2/3, but 3/2. So now you could say, well, I know that the denominator is the root, so I'm going to square root 49, which is 7. And then the numerator is the power, so now I'm going to square that and get 49. Oops, sorry, cube it. Not square it, the power is cube. And so that would be 7 cubed, not 7 squared, sorry. So maybe you were seeing this pattern, okay? So if not, we're going to generalize it right now. So if you have anything raised to a rational exponent, like a to the m over n, that is equivalent to the nth root. Okay, so whatever your denominator is, n is your root, and then your m is the power. Okay, or you could also write the nth root and the whole thing is raised to the m power. Either of those are equivalent. It does not matter how you pick to write that. Okay, so the denominator of the rational exponent is always your root. So take a second, maybe just pause the video, try these 3 questions without your calculator. Like, you should be able to think through these eventually quite quickly. So pause the video and give them a shot. So 27 to the 2/3 is really the cubed root of 27 squared. So the denominator is your root, numerator is your power. I don't want to take 27 squared, like that is huge, right? So here is where personally I would take that square and do it after the fact. It doesn't matter. So I'm going to cube root 27. What number cubed is 27? That's 3. So that's really 3, and then 3 squared is 9. Okay, same thing with 8 to the 5/3. It's really the cubed root of 8, and then to the 5th power. And I usually end with powers because that kind of blows things up, right? So the cube root of 8 is 2. And 2 to the 5th, 2 times 2 times 2 times 2 times 2 is 32. Last one, 16 to the 3/2 is really the square root of 16 cubed. And you could put a little 2 in there. Square root of 16 is 4, and 4 cubed is 64. So, kind of cool. And they're really not that challenging once you get the hang of it. Okay, then you'll be asked to rewrite using rational exponents, and then we'll find just the positive solutions, and we won't worry about the negative ones quite yet. So if you have the 4th root of a equals 14, 2 things you might notice. Well, if it's the 4th root, to undo that, I can raise it to a 4th power, because you've dealt with square roots, and you are absolutely right that I could do this and then do the same thing on the other side to undo that. Totally fine. So that means that a is 14 to the 4th power, which is a very large number. I'm just going to leave that as 14 to the 4th, but you could use your calculator if you want that expanded number. Okay, your other option, if I go back to the original question, actually I'll just erase this. If I go back to the original, I could rewrite this as a to the 1/4, and this will take us back to yesterday's lesson, right? So please remember, your root is your denominator of the fraction, and your power, there's technically a 1 there, is the numerator, right? So how do you undo a 1/4 power? You raise it to the reciprocal, and the reciprocal of 1/4 is 4 over 1. and you do that on both sides to balance, and you get the same answer, right? So a is 14 to the 4th power. So you can pick whatever works best for you. Okay, now with the second example, cubed root of c to the 8th, you could break this up into 2 steps, right? So I'll show you both ways. So I could, to get rid of the 8th power first, actually no, I'm gonna rewrite this. So this quantity is equivalent to c to the 8/3, because 8 is my power, 3 is my root. And then how would I solve for c? Well, now that I have a rational exponent, which is pretty efficient, I can just raise both sides to the reciprocal power, which would be 3/8, and raise this side to the reciprocal power, 3/8. So then, you know, power and a power from yesterday multiplies to 1, so I get c equals 47 to the 3/8. Okay, now, question, do you know what the 8th root of 47 is? No, definitely not. And do you want to cube 47 without your calculator? No. Could you pick up your calculator and type that in and get the decimal approximation? Absolutely. Okay, so you can leave your answer as is or dump it in your calculator depending on what the question asks of you. All right, let's just finish up by writing 2 expressions that are equivalent to x squared raised to the -1/3. Okay, so I could distribute the power through, and I could get 2 times -1/3 is -2/3. I could write that as 1 over x to the 2/3 to make it a positive exponent. That's kind of all your exponent rules from the previous days. I could put it into radical form. Right now it's a rational exponent, so I could change this to the cube root of x squared. Same thing with this one. I could change it to the cubed root of x to the -2nd. So all of these, I mean, I know it says 2 expressions and I just did 4, but you can see lots of different ways to write this, and there are still more. Okay, then we're going to transition into writing the equation of an exponential function now that you're kind of familiar with the idea from the last couple days. So just want to make sure you're okay with 2 key ideas when you write an exponential equation. You need to know the initial value and then the multiplier, the ratio. So those are sometimes also called the y-intercept, and if you think about the y-intercept, that's going to be plug 0 in for x to get the y-intercept. So if you go up to this equation here, if I plug 0 in for x, anything to the 0 is 1. So this is really 4 times 1, and my y-intercept is 4. Well, note, if I erase all of this, my initial value is 4. So when you have an untranslated, you know, I'm not shifting it or anything like that, your starting value, otherwise known as your y-intercept, is that initial value 4. Okay, the ratio, I think, is more obvious. It's always the base of your exponential function. So my ratio is 0.75, and my y-intercept is 4. I'll fill that in there. Okay, the only exception to this rule, if you look at the blue function, the ratio is still 3. Like, base of my exponent, definitely obvious, that's still 3. Okay, the y-intercept is not 2 on this one. So this is where you need to be careful. If you have shifting, you quite literally need to plug 0 in for x. So if I plug 0 in for x, then I get 2 times 3 to the 1st. And 3 to the 1st is 3, and 2 times 3 is 6. So just making sure you can always use your knowledge of y-intercept. Just plug 0 in for x.